Hi guys, today we'll be taking a look at some of the sources of energy that powers our lives, from the electricity you get in your home to the heating, to airplanes that take you places, etc. And basically anything that provides energy we call a fuel. So I'm going to do this in two parts. But first, let's take a look at the three broad categories of energy that powers our lives. The first and most important is the burning of fossil fuel. So I'm going to call that chemical burning. So that would be just fossil fuels. Now, of course, nowadays you can burn other stuff like biomass as well, but I'm just looking at the main sources of energy that we have. The second, perhaps most important going forward into the 21st century, is nuclear energy. And that's different from chemical energy. In chemical energy, the energy is derived from chemical bonds, whereas in nuclear energy, the energy is actually derived from within the nucleus itself, the nuclear bond. The strong forces are responsible for that. And finally, we'll look at another form of chemical energy, which is not as prevalent now, but which might also be very important going forward into the 21st century when we talk about electric cars. And this is the stuff, this is the energy that currently powers your cell phones, your flashlights, portable devices. So there'll be a couple we'll look at. We'll look at something called a simple cell. We can also have a battery and something called a hydrogen fuel cell. Okay, so those are the three broad categories that I've divided the main sources of energies that we have nowadays into. And in today's video, we'll just look at chemical burning and nuclear energy. And in the next part, we'll look at chemical non-burning. Okay, so let's get to it. We will take a look at burning. So let's look at chemical burning first. So as I mentioned earlier, this involves just write that down, chemical burning, right? So this mainly involves the burning of fossil fuels. So the source is fossil fuels, which compose coal, oil, and natural gas. Now, what happens is that we take the fossil fuel and we burn it in air. So you take the fuel, you burn it in air, and typically it results in carbon dioxide and water. And the energy that's released is exothermic. So it's going to be negative. Remember, when the enthalpy or the chemical change is less than 0, it's negative. And that heat that's given off is called the heat of combustion. So let me go ahead and define what the heat of combustion is. This is the energy released when 1 mole of fuel is completely burnt in oxygen. So I should stress this work completely. And you want to make sure, you know, it's all completely burned. So one example of this is the combustion of methane in oxygen to produce carbon dioxide gas and water. So I can balance this by putting a 2 in front here. That gives me 2 oxygens. I only have 2 oxygens on the left side. So putting a 2 there will settle everything, because I have 1 carbon on the left, 1 carbon on the right, 4 hydrogens on the left, and 4 hydrogens on the right. And the heat of combustion, the little c there, denotes the heat of combustion. The heat of combustion for this reaction happens to be minus 882 kilojoules per mole. Right? So fossil fuel has a really high energy density, meaning that just a little bit of it will give me a lot of energy. And as you can see, this is the case here. I get, you know, almost 900 kilojoules of energy from each mole of methane. That's what makes fossil fuels so attractive right now. You can carry a little bit of it in your car and it will take you a long way, right? And that's where the other alternative forms of energy have not gotten to yet. For example, for solar, we need really large areas to give us the comparable amount of energy. But as you know, research advances, hopefully we'll get to parity, and at that point we'll not have to rely as much on fossil fuels anymore. So what are the uses of fossil fuels? Well, main use is, of course, electricity. Right, this is the main form in which energy powers our lives, and this comes from the generator in a power station, which in turn comes from the kinetic energy in the turbines. And what turns the turbines? It's the steam that comes from the burning of fossil fuels. Right, so you burn the fossil fuel, which heats the water, and thereby turning the generator and giving us electricity. Right. A second important use of this is cooking. So in your home, you use natural gas, sometimes electricity, but most of the time natural gas, because food cooked using electricity doesn't taste very good. Right. And the problem with burning fossil fuel is, of course, the biggest problem is global warming. Because carbon dioxide and carbon monoxide are greenhouse gases, and you also have air pollution from the nitrogen oxides, carbon dioxides, carbon monoxides, and sulfur oxides. Those are also contributing to increasing acidity of lakes, acid rains, corals die, fishes die, etc. Right? So unfortunately, this is where we are at right now. This is our main source of energy. So looking forward into the 21st century, hopefully we'll have something else to replace that. And that's where nuclear comes in. So nuclear is supposed to hold us over until we can make solar, geothermal, and other forms of alternative energies more effective. So this is where nuclear is. Nuclear is a safe form of energy because of the technology that we've developed up till now. It's extremely safe, but we don't have uranium to last us forever. So we're going to need to look at some other alternative forms of energies. So the next up, we'll look at nuclear fuel. So just a brief introduction, and you know that in an atom we have protons and neutrons. Which are surrounded by electrons. They don't actually orbit like this, but this is just for simplicity. And then there's this glue that kind of binds the protons and neutrons together. So this glue is called the strong nuclear force. And when you split the atom via fission, so fission is splitting the atom. Right, so if I have a large nucleus and I split it, energy is released. And we can use this energy just like in a traditional fossil power station, where the energy is used to heat water. Steam produced as a result is used to turn turbines and hence turn the generator, which in turn generates electricity. So that's one way we can do it. Another way we can do it is by something called fusion. And in fusion, instead of splitting atoms, you join them. So you take two small nuclei and you join them into a larger nuclei, and as a result, energy is released as well. And you can use that energy for the same purpose, which is to heat the water in the power station, and then use that steam to turn the turbine, right? So where we're at right now is that we can do fission quite well. In fact, certain countries like France depend 90% on nuclear energy, and nuclear energy is completely clean, so it's very useful. So you take a radioactive isotope of uranium, which is uranium-235, and then you split it by having it absorb a slow-moving neutron. So that N there represents the neutron, and you're going to take that uranium, combine it with the neutron, and it will split into smaller nuclei, say lanthanum. It doesn't have to be these particular species. They could split into a variety of other species. And most important part is the energy that can be derived from this. Now, this energy is enormous, right? It's just a little bit of uranium can give you an enormous amount of energy, because according to Einstein's equation, E equals mc squared, right? You're multiplying by that c squared, which is a really big number. So even a tiny mass, m, multiplied by that c squared is going to give you an enormous amount of energy. And this is completely viable right now. We do it a lot, and it's clean. There are no greenhouse gases like in burning fossil fuels, no carbon dioxide, no acid rain, right? Because you don't get any nitrogen oxides, no sulfur oxides. So incredibly clean, and with current technology also very safe. However, having said that, it does give off harmful radiation, which can hurt humans. Therefore, the waste needs to be gotten rid of very carefully. So you need good waste management. Typically, it's buried deep underground in thick rooms filled with lead to make sure that they don't leak out anywhere else, right? So that's completely viable, but fusion is still in the research stage. This happens in the sun. Very simply, you take two hydrogen atoms and you fuse them together into a helium nucleus, and that will result in an enormous amount of energy, even more than in a fission reaction. So we could actually get fusion going, right? That's gonna last us essentially, forever, because hydrogen is freely available. You can get it from water or other sources, but right now it's not viable yet. We need very high temperatures, and you need to put more energy into it than you can actually get out of it. So it's not a very good source of energy, not yet anyway. So that was a look at nuclear fuels and fossil fuels. In the next video, we will conclude this two-part series on fuels by looking at the non-burning chemical fuels, which are fuel cells, simple cells, and batteries.